you can build a Turing machine that that works as follows. If the string belongs to the language, the Turing machine will write a yes. That's all she can do. She can say, yes, it belongs. So what if you give me a string that does not belong? She will not be necessarily capable of saying no. She might get stuck in an infinite loop, for example. Now, why you give this definition? Are there such languages? Okay, first of all, if a language is Turing decidable, then it will necessarily be Turing recognizable. If something is Turing decidable, it is also Turing recognizable. Is that true? Yes. Because if you have a machine that says yes, no, the same machine will work to recognize it. The same machine is able to say yes. It's a bonus that she's able to say no. So Turing decidable is also Turing recognizable. Okay. Now, is the opposite true? If something is Turing recognizable, okay, does it mean you can also decide it? No, and we'll see some examples. The opposite is not true. So this is not a trivial definition. Recognizable is different than decidable. There are some things I can recognize, but I cannot decide. What is the halting problem?
Finding a program will terminate.
Finding what?
A program will terminate.
Oh, right. Can you? Do you have an algorithm, right? That will work as follows. Given any program or any other algorithm, right? Or any other Turing machine, because we said those things are equivalent. So if they give you a Turing machine, and they give you an input for this Turing machine, like something on the tape. Take this Turing machine, start it with ABA on the tape. Okay? So if they give you a program and an input, a Turing machine and an input, an algorithm and a starting input, are you able to determine if that Turing machine, that program, will, for that input, will terminate, he said, or not? It will terminate, you hit the exit statement of your program, or do you have an infinite loop in there? You will get stuck in an infinite loop. Right? This problem is decidable would mean, yes, I can determine if a program for any given input will terminate or not. So it will say, yes, it terminates, no infinite loops, or no, it does not terminate, there is an infinite loop. So it will amount to detecting infinite loops. Okay. And this has, this you guess, first of all, has not been solved yet, because when you write a program with an infinite loop, the compiler cannot detect it. He only kicks you out when you run out of time limit. He will never say, oh, you got an infinite loop. So you are guessing we cannot do that, but we can prove we cannot do that. This problem is not Turing computable. This language of Turing machines and inputs that terminate is not Turing decidable. Okay. Problem not Turing computable, language not Turing decidable. Any problem can be converted to a language problem, to a string processing problem, because that's what we will process strings. Okay. So basically, the halving problem in terms of a language is this. Consider the set of all Turing machines and inputs in some alphabet. I don't care what sigma is. I is in sigma star. Where the Turing machine halts on input I. It reaches a halving state. It processes the input and halts. It reaches a halving state. This language is not Turing decidable. If I say, what language, what strings do you have here? I'm confused. What are you talking about? Well, any Turing machine you give me, right, can be encoded as a string. It's a string. We can make an agreement, okay? Like you gave me some diagram, right? If you see A or B, memorize it to W. If you see a B, you go to this state. If you see an A, keep moving right. So any Turing machine you give me, I can represent it as a string. First, I'll give you the states. Like state A, blank. B, blank, C, blank. How do you know you run out of states? Well, I'll have a special symbol, like S. This means that's the end of the stage. So if somebody says, oh, given this Turing machine, how many states you got, or what are the states? You start reading until you hit S, you see that's my states. They're separated their names by blank. I can give you the states, right? I can give you the transitions. And to some symbol T, you know that's where the transitions are between S and T. And the transitions look like, you know, that notation. The current state, what you see on the tape. Okay. Then the destination state, what you write in that position, and if you move left, right, or state, that's what the transitions look like. So I can give you the transitions. The transitions are sequences, tuples. One state, what's this? Whatever, tuple. State, symbol, state, symbol, move. All right? So I can give you all these transitions, 5 by 5 by 5. You know. Any Turing machine can be represented as a string, as a sequence. So, right? So basically I'm saying, give me a sequence, give me a Turing machine, and give me an input like ABA. This sequence will belong to the language if, when you start this Turing machine with I on the tape, it will halt. If it does not halt, it does not belong to the language. So can you detect which Turing machines halt? That's this problem, the halting problem. Represented as a language problem. All right, it's not Turing decidable. Can you prove that? No, you cannot write a program for it. Okay? So that's what we're going to do next. You can stop it. You also have to, okay, stop it. Before we prove this, let me ask you this. Consider all the Turing machines you can think of, all the Turing machines that exist. Is that set countable or uncountable? Remember at the start of the course we talked about countable sets and uncountable sets. We will use that stuff here. Also we'll use, remember we said in math there is a way, how did they prove that the set of real numbers is uncountable? It was called the diagonalization principle. Yeah. We'll use that. So the set of Turing machines, is this countable or uncountable? It's countable. I can place them in order. Turing machine 1, 2, 3, 4, and so on. Why is that countable? Well, a Turing machine is a sequence, you said, right? States, transitions, I can encode the Turing machine as a sequence. Well, a sequence is a finite number of symbols. The alphabet is finite, the states is finite, the number of states is finite. Right. So it's a sequence of sequences. It's a set of sequences. Or you can think as follows. The Turing machine is an algorithm, right? But the algorithm is a program, right? How many programs I have? Is that countable? Sure, every program you write down, if you take, for example, the ASCII codes for each input, converts to a big binary string. Okay? A, whatever, 65, whatever. So every program you write down is a binary string, a finite binary string. Okay, so the set of binary strings is countable. You have the binary string 0, all zeros. 1, all zeros 1. 2, all zeros 1, 0, and so on. Okay, so the set of Turing machines is countable. I can assign a label on each Turing machine. I have Turing machine 1, 2, 3, and so on. Now it's infinite. I have infinite number of Turing machines, but countable. Now, to what?
Do you want to turn it on?
What? It is on. Yeah, I did. Okay, so that's the first observation. Then how about, this is countable, the set of possible inputs to the Turing machine? Well, the alphabet is finite, right? So I is any string in sigma star. How many strings you have? Is that countable? That's countable. Okay. So both this set and this set is countable. So you have string 0, string 1, and so on. For example, if your alphabet is AB, okay, well, you have the empty string. That's string 0. String 1, you have the single A or the single B. So string 1, this is string 2. Then the next string will be length 2, like 2 A's. AB, BA, 2 B's. Then all the strings are like 3 and so on. I can count it. I can put it in a sequence. I can represent this. I can place this set in a sequence. Okay, so they're both countable. Now, let's take all the Turing machines. Let's make a matrix. Here are the Turing machines. You told me it's countable, so there will be a 1, a 2, and a 3, and so on. Here are all the possible inputs. The empty string, only A, only B, A, I placed them in order. Okay, here are the inputs. Okay. Now, I'm trying to apply the same proof as called the diagonalization principle. Here's what you're going to do. This works by contradiction. You want to prove that this set is not decidable, right? Okay, suppose it was decidable. So suppose the halving problem was decidable. What does that mean? There is a Turing machine that works as follows. If you give me a Turing machine and an input, this Turing machine will say yes, it halves, or no, it does not halve. For any Turing machine and any input, I can determine if it halves or not. So if this problem was Turing decidable, for any position in the matrix, like Ti, Ij, I will know if the entry is halt or no halt. I can compute every entry, right? Let's say I give you T3, that Turing machine, and I2. Okay? I could go here. I could apply, if this was decidable, this means that there is a Turing machine that decides if it halts or not. So I could apply this Turing machine that I'm supposing it exists, and I could tell you what this entry is. It will either be halt or no halt. So basically, yes, this is an infinite matrix, but any given entry I can compute in terms of halting. And every given entry will either be halt or no halt. Every given entry is computable. I know it. Right? This is a computable matrix. Okay, so if this problem was Turing decidable, I could compute any entry ij. Okay. Now consider the diagonal. What's the trick here? We did before in the diagonalization principle. We're going to build a Turing machine. If you could compute every entry, right, then we can construct the Turing machine that will be different than all of those. And that's a contradiction, because you told me here are all the Turing machines there are. So if you compute these things, then here is another Turing machine, by construction different than all of those. That's a contradiction. So what is the contradiction? Where did you go wrong? Well, in your original assumption that this is decidable. In your assumption that you can compute all those entries. That's what went wrong. So it must not be decidable. So let's go back to this. You said, okay, this is countable, this is countable. Here are all the Turing machines that exist. I enumerated them. Okay. Now, consider the diagonal. I'm going to build a Turing machine that works as follows. If T1 on I1 halts, mine will not halt. And if T2 on I2, if T1 on E1 does not halt, mine will halt. Mine will do the opposite than what Ti does on II. II. So let's call these guys instead of i's the inputs, right? X's or something. So I'm going to build a Turing machine that for whatever Ti does on Xi, my machine will do the opposite. Right? If I can do that, this is a contradiction, because this is a Turing machine, but is it equal to T1? No, because T1 halts on I1, on X1. Mine does not halt. Is it equal to T2? No, by construction, my machine does not halt in T2, but T2 halts on X2. So build a machine, M, such that if Ti on input Xi halts, then my machine on input Xi not halts. And if Ti on Xi does not halt, then this machine on Xi will halt. Now, how can I build such a machine? Okay, here is my machine. Give me input X1. Right? I will run machine T1. Now machine T1, imagine a diagram, and somewhere it says yes, and somewhere it says no. Okay? So I'll switch the yeses and the nos. So my machine does the opposite of T1, the opposite of T2, the opposite of T3. So when they give me an XI, X10, I'll grab machine T10 and run it. And if she gave you output yes, I'll say print no. And if she said no, I'll say print yes. The Turing machine is like a program, right? When it halts, it says yes, imagine a C out yes, and imagine a C out no. So I'll take T10, wherever it says C out yes, I'll change it to C out no. And wherever it says C out no, I'll change it to C out yes. So I have the dual, the complement of this machine. We said if something is Turing decidable, his complement is also Turing decidable. You can build a machine that does the opposite. So basically my machine will say no halt if you have halt, and halt if you have no halt. And this machine will be different than every single machine. Which is a contradiction, because those are all the machines there are. How come we came up with a new one that is not in the sequence? Okay. So this machine M is different than TI for all I. And that's the contradiction. See, the key, this is countable means you have, if I ask you which machine is, you have a function to compute, right? Which one is the machine in position 10? And you can tell me, oh, it has this stage, it has these transitions, that's the transition function. You know that machine in every single position. That's what a countable set is. You have a function, if they give you an index like 10, it can give you the object in that position. Right? That's what countable set means. This function is computable. Give me an index, I can specify you the object, the Turing machine in there. So therefore here, if you give me x10, and the same with the strings. They're computable means if I give you an index, who is the 10th string? You can compute it. You know exactly who is the 10th string. This is a computable function. Okay, you have the empty string, A, B, 4 of them, 2 at a time. So that's 7 so far, Who is the 10th string? So if I give you the index 10, right? You can compute the 10th string. You can compute the 10th machine. That's how this machine I constructed works. You just give me an index, 10. I'll compute the 10th string. I'll compute the 10th machine. I'll start the 10th machine with x10 on the input, with that input, and let it execute. And if we, right? But change the yes to no and the no to yes. So when she says yes, now I'll say no. What am I doing? Right? We said this is a computable problem also, so you can say yes or no in halting. If you can say yes or no in halting, right, then here is a Turing machine that says no when T10 said yes, and yes when T10 said no. And this machine is different than T10. It will be different than T9. It's different than every TI. So where is the weakness? The weakness is when you assume that you can say yes or no halt, you must not be able to do that otherwise. She could say halt or no halt. Where you say no halt, she will say halt. When you say no, halt, she will say no halt. And it's different than all of those machines. It's kind of tricky argument. Yeah.
This proves that Turing is not countable.
No, it does not prove that Turing machines is not countable. Oh, this one already proved, you see, that the Turing machines are countable. I have proven that. But I have not proven this. This is what I assume. This is what I don't know. That what I don't know is there a big Turing machine X so that if you give me T1 and X3, she can tell me halt. Yeah, she will halt. T1 will halt on X3. The assumption I made is that this is Turing decidable. I said, if it was Turing decidable, let's assume that. Well, what does that mean? This means there is a Turing machine. So if you give me any other Turing machine and any input, she will tell you halt or no halt. So let's assume there is such a Turing machine. So if I give you T1 and X3, okay, this machine, this is like a